In the previous video, what we're going to do is we're going to talk about something called formal charge that allows us to effectively look at how atoms are bonding and then based off of that decide if the Lewis structure that has that form of bonding is valid and a good way to represent how that compound looks or if it's a bad way. And so formal charge by definition is going to be the charge an atom adopts, so each of our different elements of an atom, assuming equal sharing of electrons. And then to be clear, this is not an actual charge. So not an actual charge. And so formal charge, because we have equal sharing of electrons, it ignores electronegativity. So ignores electronegativity. And so this is, kind of different than when we looked at oxidation states that took into account electronegativity. And so the way that we calculate formal charge is by taking the number of valence electrons that atom typically has, or that element, so number of valence electrons, so just for the base element, and we're going to subtract from that the number of electrons in lone pairs plus the number of bonds formed. And so sometimes you'll see this written as the number of valence electrons minus number E lone pairs plus 1/2 number electrons in bonds, or 1/2 the number of bonding electrons. I typically favor the first form, which is valence electrons minus electrons in lone pairs minus number of bonds formed. And so the best example we can use is, or the best example, one of the easiest examples we can use is that of hydrogen fluoride. And so if we draw up hydrogen fluoride, where we get 1 electron from hydrogen, 7 from fluorine, we draw each of them next to each other, we form a single bond that uses 2 electrons. We're going to use up 6 more to put lone pairs around fluorine. That's all 8. And so we can first start by thinking about what does each of these look like on their own. And so we know that hydrogen, we said, brought in 1 valence electron. Fluorine brought in 7. And so I've just given the Lewis structures of each of them. But we know when we drew the Lewis structure for the compound, we counted up the number of valence electrons. So we know hydrogen brings in 1 and fluorine brings in 7. And so for when I say number of non-bonding electrons, this is the same thing as lone pairs, or we're really looking at how many electrons are in lone pairs. Hydrogen doesn't have any lone pairs around it, so that's 0. And then fluorine, when we look at the Lewis structure for the compound, stressing that we're looking at that Lewis structure for the compound, that has 6 electrons that are in lone pairs. Then we look at the number of bonds each of these forms. Hydrogen is forming a single bond with fluorine. Fluorine is forming a single bond with hydrogen. And so we'd say that their formal charge is, for hydrogen, number of valence electrons minus number of non-bonding electrons plus the number of bonds formed. So that's 1 minus 0 plus 1. So that's 0. And for fluorine, number of valence electrons minus number of electrons in lone pairs. So 6. 6. And then plus number of bonds formed. So that's 1. So that's 7 minus 6 plus 1. 7 minus 7 is also 0. And so in this case, the formal charge on each of our atoms here is going to be 0, which is good. And so the way that we rank the goodness of a Lewis structure based off formal charge is by following 4 different general rules or guidelines. And so the first one is that the sum of formal charges for a neutral molecule, so when we look at something like HF that doesn't have a charge on the outside of it, the sum of formal charges must be 0. And so other examples are things like CO2 and CH4. Both of those must have a formal charge of 0. And we're going to use these 4 guidelines when assembling good Lewis structures. The sum of formal charges for a charged molecule or an ion, so I'll just say charged mole or ion, must be equal to charge. And so that means when we look at something like NH4 plus, the formal charges must add to +1. And when we look at something like CO3 2 minus, the formal charges must add to -2. So sum of, and formal charge I'll abbreviate as FC, of +1 and -2 respectively. The third rule is that small or non-zero, or zero, sorry, not non-zero, small or zero formal charge on individual atoms are better than large ones. And so what that means is that it's good to have many small charges are better than one big one. So if you had something that was having to add to a formal charge of -3, we're going to put -1 on 3 atoms before we do -3 on 1 atom, because it's good to spread out that electron density, kind of similar to how we talked about that with our resonance structures. And then if you can't avoid formal charge, you want to put negative formal charges on the most electronegative atoms. And that's because of their high electronegativity means that they're pretty good at stabilizing that negative charge. And you can also justify it by thinking about how good their electron affinity is. Okay? And so what that means is you're going to put negative charge on nitrogen and oxygen before you put it on something like carbon. And so these are where we're going to largely find negative charges. Okay? And so if we look at something like this right here, this cyanide molecule, what we can do is we can look at the number of valence electrons that comes from each of these different atoms. So from hydrogen, that brings 1, carbon brings 4, nitrogen brings 5. And it's the case for each of these 2 structures. And we're going to basically look at ranking each of these to figure out which one of these is correct. So in this case, instead of having, different Lewis structures, instead of having like equivalent Lewis structures like we had in resonance that had the same skeleton structure, here we can see in one case we have carbon in the center, and in the other case we have nitrogen in the center. And we're basically ranking which one of these makes the most sense. And so we're going to minus the number of non-bonding or lone pair electrons. So hydrogen has 0, carbon has 0, and nitrogen has 2 here. And then in our second structure, hydrogen has 0, nitrogen has 0, and carbon has 2. And then we're going to look at the number of bonds. Hydrogen is forming 1 bond, carbon is forming a single bond and then a triple bond, so that's 1 plus 3, so that's 4 bonds. Nitrogen is forming 3 bonds. When we go over to structure B, hydrogen is forming 1 bond, nitrogen is forming 4, carbon is forming 3. And then we're going to take our first row and then minus the second and the third. So we have, for hydrogen, number of valence is 1 minus 0 plus 1, so that's 0. For carbon, we have 4 minus 0 plus 4, so that's 4 minus 4, so that's 0. And for nitrogen, we have 5 minus 2 plus 3, so that's 5 minus 5, so that's 0. We go over to structure B, and we have hydrogen, 1 minus 0 plus 1, so that's 0. Nitrogen, 4 minus 0 plus 4. This should be 5. Sorry, so this should have been 5, and this should have been 4. So 5 minus 0 plus 4 is plus 1, and then 4 minus 2 plus 3 is minus 1. And so what we see is that in one case, we have all 0 formal charges, and in the other, we have a +1 and a -1. We've satisfied the rule that says that the sum of the formal charges for a neutral molecule must be equal to 0, so that's great, but one of these follows the third rule more than the other. So structure A, we have small or zero formal charges on all of our atoms, and that's favored. We want to have the least amount of formal charges possible, whereas structure B, we have a +1 and a -1. So wherever we can avoid forming a formal charge, we will. And so for that reason, we favor structure A. So this is our preferred structure because we have zero formal charge. Zero formal charge is best. So, and when I say 0, I mean that all of the atoms have 0. And so what I want you to do now is to look at assigning formal charges to these two structures here. So I talked about last Monday the two different ways we could write CO2. So one where we have double bonds with carbon between both oxygens, and one where you have a single and a triple. So pause the video here and fill out this table. All right, welcome back. And so what we're going to do is I'm just going to fill out this table as you just did. So we know oxygen brings in 6 electrons, carbon brings in 4, and it's the same here. So 6, 4, 6. And from here, I'm just going to complete a table at a time. So oxygen on the left has 4 electrons in lone pairs. Carbon has 0. Oxygen has 4. The number of bonds oxygen is forming is 1, 2. So 2. Carbon is forming 2 to the oxygen to the left, 2 to the oxygen to the right. So 4. This is 2. So we have 6 minus 4 plus 2 is 0. It's the same for this one. And we have 4 minus 0 plus 4. So that's also 0. Then we go to our structure on the right. We have 6 electrons in lone pairs. Carbon has 0. This oxygen has 2. This oxygen is forming 1 bond. Carbon is forming 4 bonds. This oxygen is forming 3 bonds. So we have 6 minus 6 plus 1, which is minus 1. We have 4 minus 0 plus 4. So same as before, that's 0. And then here we have 6 minus 2 plus 3. So that's plus 1. And so in this case, our preferred resonance structure is the one that minimizes formal charge. So that's going to be structure on the left. And hopefully that's also what you got. And so this is another question that I'll have you do. Pause the video here and then assign formal charge to each of these atoms. All right. So welcome back. What we're going to do is we'll assign formal charge to each one of the atoms here. And so I'm just going to write up those formal charges. If you have a question, please send me an email. But effectively, this oxygen usually wants 6 electrons because of its number of valence electrons, but it has 1, 2, 3, 4, 5, 6, 7. So this is a -1. This oxygen has the same thing, 7 electrons that it owns, so that's -1. This oxygen has 1, 2, 3, 4, 5, 6, so that's 0. And this nitrogen has 1, 2, 3, 4, so that's +1. And so if we look at our sum of formal charges here, that's +1, and then -1 and -1, so that equals a total of -1. So we should put a negative on the outside of this. And then we can assign formal charges to each of the structures below as well. And so we had the one for nitrate. Now we're going to look at N2O. And so we can assign formal charge to this one. This nitrogen owns 1, 2, 3, 4, 5, 6, 7 electrons. It wants to own 5, so that's -2. This nitrogen has 1, 2, 3, 4, so that's +1. This oxygen has 1, 2, 3, 4, 5, wants to own 6, so that's +1. We go to our next structure. This nitrogen has 1, 2, 3, 4, 5, 6, -1, 1, 2, 3, 4, +1, 1, 2, 3, 4, 5, 6, 0. And then our final structure, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, +1, 1, 2, 3, 4, 5, 6, 7, -1. And so if we look at our bottom 3 and rank them against each other to find out which one of the bottom three is the best way to represent N2O. We see that in all cases, the charge adds up to 0. So this one adds up to 0 because we have -2 plus 1 plus 1. This one adds up to 0, and this one adds up to 0. And when we look at each of these, we can see that our structure on the left has everything has a formal charge. And so really what we're having happen here is that we're breaking rule 3 because we're having so much formal charge that it's crazy. Whereas our other two structures, we have at least one atom that has a formal charge of 0. And so when we look at ranking structure 2 and structure 3, what we end up seeing is that the only difference between the two is that in structure 2, the nitrogen has the -1, and in structure 3, the oxygen does. And so when we think about our fourth rule when looking at formal charge, we said that we like to put negative charge on the most electronegative atom or atoms. And in this case, when we look at the electronegativity of nitrogen, so the En of nitrogen is 3.0, and that of oxygen is going to be 3.5. So this is oxygen. Oxy equals 3.5. So in that case, we favor putting the negative charge on the oxygen over the nitrogen because it's more electronegative. So we would say that our preferred structure here is going to be this one right here because it minimizes formal charge and it puts that -1 formal charge on the most electronegative atom.